Imagine a world where the sky is not the limit, but just the beginning. Welcome to the science of rockets. Rockets, the magnificent machines that bridge Earth to the cosmos, have evolved remarkably from mere fireworks in ancient times to the colossal vehicles that now pierce the heavens. Through a melding of fiery passion and precise science, these towering structures embody humanity's relentless quest to explore and inhabit the unknown. Now let's ignite our curiosity as we trace back to the origins of rocketry. Our journey begins with visionaries who first dreamed of space. Among them, Konstantin Tsiolkovsky, the Russian scientist who is often dubbed the father of astronautics. His most profound theory, the rocket equation, is still used today to calculate the velocity and movement of rockets through space. Tsiolkovsky imagined a future where humanity would colonize the cosmos, using rockets powered by what he described as metallic powders. Across the globe, an American contemporary, Robert Goddard, brought these theories to life. Often working in seclusion, Goddard successfully launched the world's first liquid-fueled rocket in 1926. This event marked a seminal moment in rocketry, proving that controlled spaceflight was more than a pipe dream. These early pioneers were not just theorists and tinkerers, they were dreamers who bridged the gap between fantasy and reality. Through their relentless pursuit, they crafted the first pages of our now burgeoning story of space exploration. These pioneers set the foundations, turning what once seemed like fantasy into tangible science. What propels a rocket into the vastness of space? Let's break it down. Imagine a skater pushing away from a wall. As they push the wall pushes back with equal force, sending the skater gliding across the ice. This is a perfect demonstration of Newton's third law of motion. For every action, there is an equal and opposite reaction. Rockets operate on this very principle. When a rocket expels its exhaust downward, that fast-moving exhaust pushes the rocket upwards with equal force. Let's delve a bit deeper into the mechanics. The rocket's propulsion system ejects mass in the form of high-speed gas. According to the conservation of momentum, the momentum lost by the gas must equal the momentum gained by the rocket. This exchange propels the rocket forward, allowing it to soar through the atmosphere and into space. But how does this momentum exchange occur? It begins in the combustion chamber where the fuel and oxidizer react violently, creating hot gases. These gases expand rapidly and are funneled out through a nozzle, accelerating them to speeds that can exceed the speed of sound. The force generated by this high-speed expulsion of gases is what thrusts the rocket upward, overcoming the pull of Earth's gravity. This interplay of forces and momentum is not just about moving upwards, it's about attaining the speed necessary to break free from Earth's gravitational pull, termed as the escape velocity. Achieving this speed is crucial for the rocket to enter orbit around Earth or travel to distant planets. With these principles, rockets defy Earth's gravity, reaching for the stars. Every rocket is a symphony of technology, precision, and innovation. Let's dissect this marvel, starting with the payload. This is the heart of the mission. Whether it's a satellite, a scientific instrument, or humans bound for new frontiers, it's what the entire journey is designed around. Next, we have the propulsion system, the muscle of the rocket. This system, which includes engines that burn fuel to create thrust, works on the principle of action and reaction. It's what lifts the rocket off the ground and propels it through the atmosphere. Surrounding this muscle are the fuel tanks, the reservoirs holding the rocket's lifeblood. These tanks store the propellant necessary for the engines to function. The dance between weight and balance here is critical. Too much fuel can weigh down the rocket, too little, and it won't reach its destination. Lastly, the guidance system. This is the rocket's brain. It navigates the course, ensuring the rocket follows the correct trajectory from launch to orbit and beyond. Understanding these components helps us appreciate the complexity and beauty of rocket science. Rocket engines are the heartbeats of every space mission. These remarkable machines are not just powerhouses, but are tailored masterpieces of engineering designed to defy Earth's gravity. Let's delve into the two primary types: liquid and solid fuel engines. Liquid fuel engines, like those used in the Saturn V and Falcon Heavy, mix liquid propellants, typically hydrogen and oxygen, in a combustion chamber. The beauty of these engines lies in their controllability. Thrust can be adjusted, stopped, or restarted as needed, providing flexibility during flight. On the flip side, solid fuel engines offer simplicity and reliability. Composed of a solid propellant mixture, these engines ignite once and burn until the fuel is expended. They're perfect for booster stages where straightforward, robust power is paramount. However, their lack of throttle control makes them less adaptable than their liquid counterparts. Both engine types have their unique roles, playing to their strengths according to mission demands. Each engine type brings us closer to understanding and harnessing the power needed to explore outer space. The launch of a rocket is a culmination of years of planning and precision. Picture this: a rocket stands ready on the launch pad, towering against the sky as the final countdown begins. At ground control, a team of engineers and scientists monitor every parameter with eagle-eyed precision. Communication is key, and the air is thick with anticipation. The countdown is not just a timer, it's a series of meticulous checks and balances. Fuel levels, engine temperatures, weather conditions, every detail must align perfectly. It's a dance of technology and teamwork where even the smallest oversight could delay the launch or worse, jeopardize the mission. As the clock ticks closer to zero, astronauts aboard the rocket make their final preparations, their training and instincts guiding them through these last crucial moments. Tension rises, the final 10 seconds feel like an eternity. Then, ignition. Flames roar as the engines come to life, and the rocket begins its ascent, climbing higher and higher, carrying the hopes and dreams of humanity into the boundless expanse of space. Every countdown echoes the pulse of human ambition reaching for the cosmos. Space is an environment full of wonders and dangers. As we venture beyond Earth, we encounter unique challenges that demand extraordinary solutions. Among these, microgravity presents a peculiar hurdle. In the weightlessness of space, both the human body and equipment behave differently. Bones lose density, muscles atrophy, and fluids in the body redistribute, posing significant health risks during long-duration space flights. Then there's the ever-present threat of cosmic radiation. Without Earth's protective atmosphere, astronauts are exposed to high levels of cosmic rays that can damage DNA and increase the risk of long-term health issues, including cancer. Engineers counteract this by designing spacecraft with specialized shielding and monitoring radiation exposure closely. And let's not overlook the vacuum of space, a realm devoid of air and pressure. This extreme environment can cause immediate peril to both astronauts and their spacecraft if not properly managed with robust spacecraft designs and rigorous safety protocols. Overcoming these obstacles is part of our quest to explore beyond our earthly confines. As we stand on the shoulders of giants, what does the future hold for rocketry? The next chapter in our cosmic adventure is fueled by breathtaking innovations and bold dreams. Imagine rockets that not only reach the stars, but also return to tell the tale. Reusable rocket technology is revolutionizing our approach, making space travel more sustainable and cost-effective. Envision a world where Mars is not just a distant red dot in the night sky, but a destination. Colonization missions to Mars are becoming more than just science fiction, with plans for sustainable habitats and life support systems. These endeavors could transform humanity into a multi-planetary species within our lifetimes, and there's more on the horizon. Breakthroughs in propulsion technology like nuclear thermal rockets promise faster travel times, opening up the possibility of exploring even more distant worlds. The future of rocketry promises to elevate humanity to new cosmic heights. As we harness these technologies, the cosmos might just become our next home, our new frontier. As our journey through the science of rockets concludes, remember, this is just the beginning. Throughout this exploration, we've traced the arc of rocketry from its earliest visionaries to the intricate dance of launch procedures. We've delved into the principles of propulsion that defy Earth's gravity, and we've dissected the anatomy of these incredible machines that carry our dreams beyond the blue. We learned that rockets are not just assemblies of metal and fuel, but the culmination of human curiosity and ingenuity. Each component, from the smallest valve to the roaring engines, plays a pivotal role in piercing the celestial veil. We've seen how challenges like cosmic radiation and the vacuum of space are met with resilience and innovation. As we stand on the precipice of tomorrow, let's carry forward the spirit of exploration that propels these marvels of engineering. Continue to educate yourself, stay curious, and dream about the vast cosmos. Keep looking up, for the stars are only the beginning of our cosmic journey.